So I will tell you about the problem that has been my main concern for the past few years, 4 years. Hello. It is a single problem. It is a path TSP. You probably heard about the TSP, and the path TSP seems to be an innocently different variant when the salesman doesn't want to arrive to the same point where he started from. When I first heard about this from David Schmois in Oberwolfach, I thought, well, isn't it trivially reducible? And I had immediately 3 force reductions to the ordinary TSP. That you can have as good an approximation as for S equal to T. Why would it be such a big difference if S is not equal to T? And indeed, it might be not such a big difference, but so the thing is about it, just to tell right in the beginning where is our sensitive region, is that there is no 3/2 approximation, contrary to what you probably, most of you heard about Christofides heuristic. When S is equal to T, you have a 3/2 approximation. We'll sketch it. We don't have that. The same kind of approximation gives 5/3. There is no easy reduction. But indeed, it might be that, that to reduce 5/3 to 3/2 is an easier task than to reduce 3/2 to less than 3/2. There is no progress in the general TSP for 3/2 from 3/2 since 40 years. On the other hand, there is progress from 5/3 down, and the theorem, and we are quite close now. We are at 1/34 from 3/2 from the goal. So, but not completely trivially. So. That's why I like to talk about this, because of course I can't tell a full proof in 1 hour, but if I communicate some of the ideas, that's already good, because these ideas can be used for other problems as well. And some of you might be tempted to have, maybe we just overlook something, and that would be a great result to cancel that 1/34. We just finished the research a month ago, and we didn't want, we had it already 2-3 months ago, but we didn't want to finish the paper because we always had one more temptation to get rid of that one, +1, ugly +1/34. I think we get the sense, but somehow we...
Is 1/34 really tight estimation from your...
Yes, we need we everywhere have, we try to exploit all the ideas, and we couldn't get better, so now we put on archive in the beginning of April. I went to Shonan, and I thought it's better to put an end, but yes, we can't. Actually, it comes out in a bit less ugly way. It's that 1/34 in another, directly where it comes out, it's 1/16, which is a power of 2. And then it is transformed to this bound of 1/34 for the general problem. Anyway, okay, so I will have a little appetizer. Well, this is not an appetizer, maybe a disappetizer, a little technical. So the fractional relaxation of the problem, natural fractional relaxation, that is considered from the beginning about the problem, is that the sum over all cuts. So you take random, not random for the moment, you take variables for each edge of the graph, and you write that the sum on every cut is at least 2, on every cut not separating S and T. You want at least 2 edges, an ST tour will take at least 2 edges for every cut which does not separate S and T, and at least 1 for every cut separating S and T, and on vertices we want equality. So this describes the integer solutions of this linear program will be the Hamiltonian path between S and T, right? In every vertex we want 2, and except S and T where we want 1. The sum of the variables be 1. So this is the fractional relaxation. This means the sum on this cut, and we want 2 if S and T are not separated in 1. if they are separated. Okay, so integer point or Hamiltonian paths, and optimum is the optimum ST path length, opt LP is the optimum of the fractional relaxation. Okay, now we reformulate it, and this will be more fun because we see again our salesman and postman that I spoke about already in the colloquium talk, but now we'll see them in an advanced way. I don't speak about the postman problem only indirectly, only as an auxiliary tool to solve the salesman problem. On the other hand, the postman will be a help for the salesman, and the reformulation that we'll consider is the following. So far we wanted each vertex to be visited exactly once by the salesman. With the help of the postman, we'll consider a little different problems where every vertex is visited at least once. Plus, we will want fixed parities in every vertex, even for vertices different from S and T, and odd for vertices S and T. And this is the same problem. And the reason the two are the same, so we want I will show you why. If we have not a solution of the postman problem, we don't have to go through every edge at least once, only through every vertex at least once. I should have written here through every vertex at least once. Plus, having the parity constraints, we know that if we have such a graph that our salesman goes through every vertex at least once and the parities are good, then we have a postman tour of length at most as much, because the salesman can follow the postman whenever it reaches a new vertex. It follows him. It goes exactly to the same vertices unless he goes back in his Eulerian tray of a subgraph to a vertex that he already visited. He waits, and whenever a new vertex is reached, he goes directly to the new vertex. Okay? Now, if your function is a metric which was always written, and I also said a week ago, but I didn't repeat now, so we need a metric function. Otherwise, any approximation to the traveling salesman problem contains the Hamiltonian path problem, so it's NP hard. If you have a metric function, then it will be shorter. The shortcut that the salesman uses will be shorter than what the postman does. And conversely, if you have some tour like this, after taking the metric closure of the graph, because there we don't ask, the advantage of this formulation is that we don't need to have a metric function. But if you take the metric closure and you just solve this problem, then you can, instead of each edge, get back the shortest path between the two endpoints, and you don't change the parities, and you will have a solution of that problem. So the two problem is just an easy exercise to show that the two problems are equivalent. The metric TSP, when you visit every vertex exactly once, and the version where you visit every vertex at least once, and you ask that you touch every degree with an even number of edges, except S and T with an odd number of edges. Okay? So to be precise, this is the problem that we'll study, because it is much better. This postman-like salesman problem. So we would like a minimum ST tour. We have two vertices of the graph, and we want a shortest Eulerian sub-multigraph. A sub-multigraph means that every edge of the original graph is 0, 1, or 2 times in our tour, so we can delete edges. That's the difference between the postman problem. The postman has to go through every edge at least once. We don't want to go through every edge at least once, through every vertex. So it's a connected graph, and we would like a shortest Eulerian, which means connected, and all degrees even except S and T, which are odd. And then it will automatically, every vertex will be touched automatically at least once, so we didn't have to repeat this here. This is our problem. This is the problem we'll spend 1 hour with, so you had better ask a question if you don't understand, because then you will be bored. So yes?
Oh, yeah, go ahead.
Please say it again. So a subgraph, so we can delete edges or we can insert.
We can delete edges, we can just leave edges, and we can have a second copy of every edge. We don't, initially you could think that you can triple or quadruple, but it's not worth because you delete two copies and neither parity nor connectivity change if you delete two copies. So indeed, you can think about it like that you take 0, 1, or 2 copies of every edge, which is not written here because it follows actually from minimization that you won't have more than 2 copies, but it will be the case. So we need 0, 1, or 2, multiplicity 0, 1, or 2 for every edge to keep connectivity and to have the good parity. That means that's what Eulerian means. So that means connectivity plus parity of the vertices. Okay.
In such a way that all degrees become even?
Or that all degrees become even except S and T, which become odd. Because we want to start, and that's the condition. Euler's, the fact that in the graph we construct there is an Euler trait, Euler did the work. So we don't want to do that work again. So we only care to have a subgraph with every multiplicity 0, 1, or 2, where every degree is even except S and T, which are odd. Good.
So you cannot reduce, I mean, if I add an edge from S to T.
Yes, what will be the weight of that edge? Yeah, anyway, that was my way, Oberwolfach at lunch, and actually my co-author Anke van Zeilen was at my table, and she was finding counterexamples to all the ideas I had, but indeed, it's very tempting, but you can't do that because
that's not a metric, or
it's a metric. No, even if it doesn't, you can suppose it's a metric. You can, but you don't have to, because if you don't have a metric, you can take the metric closure, and that will be the same problem. For this version, it's so the advantage of not requiring to be a metric is that, for instance, this problem has a cardinality version. The TSP, you don't have a cardinality version. All TSP tours have the same cardinality. The minimum cardinality of such a tour, it corresponds to the minimum weight tour, where the metric is the distance metric of a graph. And for that, actually, that's how I started to deal with the TSP problem. We have a better approximation guarantee than 3/2. We have a 7/5, 1.4 approximation guarantee for graph metrics, even if S is equal to T. But let's not. So if you add one additional edge, you want to force the traveling salesman to go through that edge, and then in order to define the weights, indeed, either you won't have a metric, or it won't correspond to an unoriginal tour. So I don't want that really takes. Then we are late for dinner. But indeed, it's good to try, and I would, out of the seminar, I am ready to tell the counterexamples, some of them that my colleagues told me, or maybe some others, why it can't be reduced, just simply reduced to the S equal T case. Okay? So the multiplicity 0, 1, 2 are there, that actually you can restrict yourself to that, that's evident. Okay, so metrics, we forget about metrics. That's quite hard to use. People usually are used that you have to have a metric. Yes, if you want every vertex visited exactly once, then you have a metric, but we don't have that problem. We have the problem of Eulerian submultigraphs, right? So this was as appetizer, and I hope your appetite is still not decreased, but increased. And now some preliminaries. We actually, so T-joins. T-joins, parity correction, random sampling, narrow lonely cuts edges. So we have quite some notions to, but they are quite fun notions to go through. And the fractional relaxation I already spoke about. It just maybe for the notations that I rewrote it, that X star will denote the fractional optimum, so the optimum of this linear program, which is the natural linear programming relaxation of the problem, and that's all. And we can suppose that our edge set is just the support of this fractional solution, so we don't have other edges. This is also a difference with metrics. With metrics you have a dense graph. You need the complete graph, right, in order to define a metric, but we don't have the complete graph. We have just the graph which is the support of the fractional optimum. And also the problem definition, everything, even the weighted one, can be defined for not the complete graph. It has many advantages to take this version, the Postman version of the Salesman problem. Yes, Sangil?
Yes, so this polyhedron, the polytope, is from the initial description of the problem, not from the reformulation.
Right. When S is equal to T, there was a similar one, the sub-2 elimination polytope, which is very similar to this. This actually I saw this polyhedron for the first time in Kleinberg and Schmoiss's paper, which is the first recent paper about the Salesman problem, and this is how they described it. But indeed, this is the natural corresponding version. So the only difference there that every cut has to be intersected with at least 2 edges, so the sum of the variables on every cut is at least 2. That's the sub-2 elimination, sometimes called Held-Karp relaxation. And that's the famous linear program to which the integrality gap is compared. And now for this problem, this is the one which is more recent, but indeed this is the natural relaxation. It's a polyhedron on which you can separate since you have cuts. The separation problem is just to minimize on cuts. There is no combinatorial algorithm though, even if S is equal to T, so there are open problems related to this polyhedron, but anyway you can in polynomial time optimize on it. Okay, so T-joins, we just did it at the course, so I could ask one of the students of the course to tell it, but since we have time restriction, I will tell it. So a T-join is a subset of edges which has given parity in every vertex, and the parity is given by T. So T is a subset of the vertices, and T-join is a subset of edges, so that the odd degree vertices are exactly the vertices of T. Okay, for those who yes? Okay, so here is, for instance, a T-join, where T is the set of odd degree vertices, is the whole vertex set. I always, do I have a laser? Yes, yes. So T is the set of all vertices of the graph. And here is another one, so not necessarily a matching, and it can have smaller weight if for some weighting of the edges. It can have a smaller weight. So why do we care about T-joins? Well, we have a connectivity constraint and a parity constraint. So, and already the classical algorithm that I already mentioned and that we all sketched, Christofides algorithm, separated the two. First cared about connectivity, then about parity. And in order to satisfy the parity, we need to change the parity. Now, T-joins are the right tool to change the parity, right? If you have a T-join and you add it to your graph, or you add a second copy for each edge of a T-join, then you will change the parity exactly in the vertices of T. Then the parity of the degrees will change exactly in the vertices of T, right? But you can also delete. So you either add or delete edges in a T-join, and both will have the same effect to change. If you add an edge or you delete an edge, it changes the parities in the two endpoints, right? So we have the freedom to add or delete, but deletion affects connectivity as well, so we have to be careful. Addition doesn't affect connectivity, but more recently the new results include deletion as well, and we will also delete as well. So now easy things that we checked at the course, that if G is connected and T even, then there exists a T-join. those who don't know can have fun with at home and check it. You can determine, so please accept this, because at the course we have more time. There we could almost do it, but here not. You just please accept that you can find a minimum T-join in polynomial time. For arbitrary weights, actually, but we need it for non-negative weights. You can find it in polynomial time. It's matching theory. It can be reduced to minimum weight perfect matchings. And another remark about T-joins, that if you take the symmetric difference of 2, which is the same as the mod 2 sum, then in every degree you take the symmetric difference also of the 2. So the symmetric difference of a T1 join and a T2 join will be a T1 plus mod 2, so T2 join, so T1 symmetric difference T2 join. Okay, and another one more remark, that what we are looking for is a minimum weight ST2, right? A minimum weight connected graph. So ST2 means connected graph which has the right parities in every vertex, so even besides SNT and odd in SNT. And such a thing is a spanning tree plus a TS symmetric difference ST join, where TS is the set of odd degree vertices of the tree. It has always of this form. So if something is a ST2, if and only if it consists of a spanning tree plus no deletion plus an ST2 doubled or taken from other edges of the graph. So plus such a join. Why is it true? Well, if you take pardon? TS is the set of odd degree vertices of the tree. G is always the set of odd degree vertices of the graph G. Why is it true? Well, if you take a spanning tree and you don't delete any of its edges, your graph will be connected, right? Now, if you change the parity in TS, every degree will be even. So if you add a TS join, then every degree will be even, but it is not a TS join that we add, but a TS symmetric difference ST join, then every degree will be even except SNT, which will be odd. So this will be a connected graph with exactly SNT as odd degree vertices. And then conversely, if you have a connected graph with this property, so if you have an ST tour, then you can take an arbitrary spanning tree. It has a spanning tree since it's a connected graph, and the rest of the edges, so those that you doubled and those which are not in the, all edges that are not in the spanning tree, will form, since the degree parities are good in your tour, plus what remains besides any spanning, besides the spanning tree S that you took, is such a join. So what we are looking for is exactly something which is a tree plus an TS symmetric difference ST join. Of course, it's not unique, this tree S. You have many trees S in a tour, but we can, looking at the solution in this form is not a restriction of generality. A solution looks like this. And that's just an illustration of the degrees. Let's not care. So let's finally sketch what I promised already several times, this Christofides 3/2 heuristic. Well, he takes a minimum weight spanning tree for just the weights that we have. This is 76, so, and no progress since then. So just take a minimum weight spanning tree and a parity correction, a minimum weight TF join, or TF, well, it is for S equal T, Christofides heuristics. Sorry, I should have written that on top of the transparency, but I copied it in the last minute, this one. So S is equal to T now. I write it on the blackboard, and then I erase it. So for temporarily, we have S is equal to T, just to revise. We have we take a spanning tree and we parity correct it. So we take a minimum weight in an optimal way. That is, we take a minimum weight TF join. Here is the tree F all degrees are odd, like in the whole graph. And here is a minimum, well, but it depends on the weights, but here is a TF join. Let's suppose it is minimum. I don't want to bother about weights here. And now the minimum spanning tree is smaller than equal to the optimum, right? Because the optimal tour also contains a spanning tree, and we have the minimum one. So ours is certainly smaller than the optimum. And the minimum parity correction is also smaller than the half of the optimum. Why? Because the optimum, let's imagine it, we don't know what it is, but we can imagine it, it is here, it's a connected graph. And so it contains a T-join. So optimum is a connected graph, it contains a T-join. And all its degrees are even, because S is equal to T, so all the degrees of this optimal solution that we imagine are even. And it's connected, so it contains a T-join, and since all degrees are even, the complement of this set with respect to this optimal solution is also a T-join. So it contains two, it can be partitioned to two disjoint T-joins. It's a connected graph, it has a T-join, the complement of the T-join with respect to this optimum is also a T-join. So this optimal solution can be partitioned into two disjoint T-joins. One of them will be at most the optimum, so the optimal T-join, at most half of the optimum, so the optimal T-join is at most half of the optimum. Not, if, yes?
Any drawing, can you?
Yeah, well, let's make it simple and let the, here is the optimal tour. Well, all degrees are 2, it's not necessary, it could be that they are bigger. And then, since it's a connected graph, it contains a T-join. Well, T comes from the T, we don't care, but we have a T-join. Like, it can be, in our case, T is equal to V, so a matching is an optimal T-join. And the complement of it with respect to our optimal tour is also a T-join. The rest of the edges also forms a T-join. Since they have they satisfy the parity condition, so the set of odd degree vertices is T, and in the tour the set of odd degree vertices is the empty set. Every vertex is even. So even minus all degrees equal to T is something in the set of edges where all the degrees have the degrees have the same parity as T, so it's also a T-join. Anyway, if you just remember this, that an optimal tour, since it is connected, has a T-join, and because of this it can be partitioned into two T-joins, then you have that the minimum of the two T-joins will be at most the optimum. And because of this, you have a 3/2. It is not taught like this, it is with matchings, but then you have to take the metric closure, and it is this the sense of Christofides, even if he maybe didn't know this, because he spoke about matchings, but it is to correct parity, and you can correct parity with at most 1/2 of the total, with 1/2 of the optimum. Okay? The same you can do for the ST problem with 5/3 only. And this is a little bit more difficult. Actually, there is a paper about it, and not so easy paper, but the thing is easier than what stays in the paper. It is Holgavin's paper that noticed this, that this type of algorithm gives 5/3 for the ST path problem. And here, actually, it's also good to teach when one has time in a course for approximation algorithms. And why is it 5/3? And why not better? So for a long time, for 20 years, this bound could resist this 5/3 bound. And here the reason is that So again, the algorithm is the same. You take a minimum spanning tree, and that's still true, that the minimum spanning tree is a lower bound for the optimum, right? Because an optimum tour contains a spanning tree, so that part is still good. But the parity correction, and it is still true that it contains a T-join, but it's no more true because of this ST, that in an optimal ST tour, if you delete a T-join, the complement will not be a T-join. So we can't say that it's at most 1/2 because of this. So you can choose a parameter and then find that that parameter should be 1/3 in order to find the optimum, but we will already choose the 1/3, and you will see that everything works out if you have 1/3 already. So we just take the right minimum join, not TF join, because if you take a minimum TF join, then every degree will be even. But now you take a minimum TF symmetric difference ST join, which are the red in a tree. If you take all the edges except the ST path, and you double those. Many of you may know a 2 approximation algorithm, which consists in doubling all the tree. That's twice the optimum. That's a tour which is twice the optimum if S is equal to T. If S is not equal to T, and that's interesting, because if S is not equal to T, this tree doubling algorithm is better. You don't have to double all edges. You don't double the edges which are on the ST path. And then the parities will be good. So if you take any tree, there is a unique ST path on it, and you double all the edges which are not on the ST path, then all the degrees will be even except the degree of SNT, which will be odd. And this is a good solution. And this is one of the good solutions. And now we will find another reason to estimate, which is a little bit more complicated than in the S equal T case. So if this tree that you have doubled, the edges which are not on the ST path, is at most 2/3 of the total weight, then we are done, right? So we can suppose that it is at least 2/3. So we can suppose that the ST path is at most 1/3 of the total weight of the tree. And also we can suppose this in the optimum, because the optimum ST tour, it is not the union of two parity correcting joins, but it has a parity correcting join, and its complement, what is it? Since itself it has two odd degree vertices, so you add mod to this, the incidence vector of this, and of S and T, so the complement of such a join will be such a join. We have to keep in mind that an operation with an edge set can be projected to an operation on the vertices, right? So if we have an optimum ST tour where the incidence vector of the parities is S and T, and we take the complement of such a set, which means a subtraction mod 2, then the complement will be a TF join. And so this is also at least 2/3 of the optimum, and that means that this is at most 1/3 also. So we have a path which is at most 1/3 of the optimum, and a TF join which is at most 1/3 of the optimum. And the symmetric difference of the two will be at most 2/3, at most the coordinate of the union, at most 2/3 of the optimum. And therefore, we have that we can always parity correct with at most 2/3. So we lost a little bit. We lost 1/6 compared to the Christofides case. And if you just remember the elements, you can reproduce this proof. I think it's quite natural too. Okay, but this is not our main goal, and we have about half an hour, which should be good to communicate the ideas of the rest. Let me just mention that not only that the minimum T-join, so minimum parity, minimum subgraph, minimum weight subgraph satisfying parity conditions can be solved, but their convex hull plus the non-negative orthant. So the polyhedron, which the linear program, which has integer vertices and which corresponds to the optimum of the parity correction problem, is also described. And it is described by cut constraints, and summing the variables to be, and the sum of variables to be at least 1 on this cut type constraint. This is what we should know and accept, that on some kind of cuts we need at least 1 in order to be in the in order to be in the convex hull plus the non-negative orthant of parity correction H sets. Now, a trick that we exploited already in some exercises at the course is that if we show a vector in the polyhedra, then we know that the optimum, and if the optimum is integer, we know that that integer vector is smaller than the value, than the objective value of the vertex that we have shown. We saw for bipartite graphs, regular bipartite graphs, such a vector, which was in the convex hull of matchings, and then we knew that there exists a matching which has smaller weight than that vector. So if we have something in this polyhedron whose constraints are like this, some on cuts at least 1, then we will have a parity correction vector which is which has weight as much. And this is another proof, instead of Christofides, a non-combinatorial proof. We had a simple combinatorial proof in a minute, and now we see again a little bit better bound, because it says that if we have the optimum of the fractional relaxation of our problem, then the half of it, the half of that vector, is in the parity correction polytope. So we can correct for every t, because on every cut this will be at least 1 if s is equal to t. And then you can correct parity for this price, which means that not only at the optimal tour is at most 3/2 of the optimum, but it is also at most 3/2 of the fractional relaxation of the optimum, which is a smaller number. So this gives a little bit better bound by Woolsey if s is equal to t, and for us, but what is the problem for us? Why can't we just copy this and have 3/2?
You get a half, right?
1/2, and for cut separating S and T we only have 1. Before we had at least 2, so the 1/2 was in the T-join polyhedron, but now for cut separating S and T we have only 1/2, and so we are not in the T-join polyhedron, and this is what we have to repair. Now, one idea, so let's which arose for the S equal T case, where for graph metrics they had 3/2 minus epsilon, a little bit better than 3/2, not for arbitrary metrics, just for these graph metrics, where the metric function comes from taking the shortest path of graphs. So all one weights, and you take the shortest path. That's what it concerns. And they, for this problem, they considered for the first time this method of interpreting a convex combination as an average of so as an expectation of a random variable. So, in other words, the following is the remark that x star, if it is in this fractional relaxation of the traveling salesman problem, then it is also in the convex hull of spanning trees. With a little mistake, but let's not be as fancy right now, as refined. So this x star is a convex combination in the convex combination of spanning trees. Actually, for our ST path problem, it is precisely true that our x star the fractional optimum of the problem is in the convex hull of spanning trees. And this uses something that we will learn at our course, the matrix partition theorem, the spanning tree, the convex hull of spanning trees, or actually maybe you have learned already, because the matrix polytope, you don't need, in order to determine, to write X star like that, you need matrix partition algorithm, but in order to describe the basis polytope, it is enough to know what is the convex hull of independent sets of a matrix. So anyway, X star satisfies those conditions. It is in the convex hull of spanning trees. And if it is so, then we can write it as a convex hull of spanning trees, which means sum of lambda I, the characteristic vector of spanning trees, where sum of lambda I is equal to 1. Now, sum of lambda I equal to 1, it means that the lambda i's can be interpreted as the probabilities of a probability distribution of a random variable, of a spanning tree valued random variable, and you take each spanning tree with the probability of its coefficient, right? So the coefficient in this convex combination is the probability of taking that spanning tree, and then X star E will be the expectation of an edge, the expectation of an edge in this random spanning tree. So you look for each edge, whether it is in the spanning tree or not. You take 1 if it is, 0 if not, and you take the expectation of this random variable. That will be X star of E, which is equal. But yes?
Why is the number of spanning trees polynomial?
By Carathéodory's theorem. So when you take a convex combination in n-dimensional space, you will have for every vector a convex combination which has at most n different. So here the space is the edge space, so it's not nm. The number of edges, you will have as many non-zero coefficients for your spanning trees as the dimension of the space, right? For a fractional, and even for integers, actually, you can have a bit more, but and also polynomials. So linear programmers know this as if there exists a solution, then there exists a basic solution with linearly independent extreme rays, right? You heard all about, in some form, about this theorem. And now, okay, what did I want still to say is that our notation, I won't introduce one by one all notation, but for instance this, we have now this random tree from our combination, and the SST will mean the ST path of each tree. So this is a random tree, and we can take an ST path in this random tree. So this means that if we sample the tree S, then we take the ST path in our tree that we sampled. Okay, and the complement yeah. So these two sets will play a role for each tree, the ST path and its complement. And we will also use the random versions of it, which means whenever this S is equal to a given tree, then we take these two sets. And the expectation, they both have an expectation, P star and Q star. So P star is the expectation of the ST path part, Q star of the complement, and these are two different quantities. The expectation of one, so X star, or optimum, can be decomposed into P star and Q star. Okay, so shall I go back? Is it okay? Okay, so now we have to deal with this problem that our X star is deficient on cuts which separate S and T. That we can't take its half. We want to complement it so that it still is at least 1 on every cut. And so let us see this on this example. A cut is called narrow, actually by our predecessors, Kleinberg and Schweiss, this famous paper which after 20 years made the first improvement. I will at the end speak about history, but I didn't want to spend time. First we work, and then we speak about history when we are tired already. They defined narrow cuts, those which are smaller than 2, right? If S is equal to C, we don't have such cuts. That's why we can take 1/2. And now these are the guilty. These cause us problems. They are smaller than 2. Now, these cuts, if you divide X star by 2, they will be smaller than 1, and you won't be in the right parity correction polyhedron. So, now if we reverse the, if we start with probabilities, and it is luck, we sample our trees, what is guilty for a cut to be narrow? If all the trees have at least 2 edges in this cut, then the expectation will be at least 2. So the convex combination will also be at least 2, and then X star will be good. So the guilty for a cut to be narrow is that it is lonely in some trees, right? Every tree intersects every cut in at least one edge because it's connected, but many trees are intersecting it in only one. It's bad luck. They are the guilty trees. They are the bad luck because they intersect the cut in only one edge. But there might be some in our convex combination, and this is the source of all the problem and difficulty in this ST path TSP problem. And so we call it lonely edge if a tree has only one edge in a cut. That's a lonely edge, and that's a lonely cut for this tree, and so on. So can you tell what are the lonely cuts here? Yes, you can, because they are the pink ones. They are the pink ones in this tree. So the tree was, let me just go back. The tree is not clear. So the tree is this path plus one edge. That's the tree. I probably erased it at some point. And these are the lonely cuts. These are the cuts that have a deficit in this graph. So here is the vector x star. This is in the polytope. X star is 1/3 on the very thin edges, 2/3 on the bit thicker edges, and 1 on the black edges. And these are the edges, these are the narrow cuts. The pink ones are the narrow cuts, which have a deficit. If you add up the weights, they are less than 2. And in this tree, these are the lonely ones. The good thing about the narrow cuts is that there are not many. They form a chain. That's also something that they proved already, our predecessors, that they always form a chain, and they separate S and T, of course, because cuts which do not separate S and T, they have X star value at least 2. So they separate S and T, and by a simple application of submodularity, you get that they form a chain. So there are not only nested, more than nested. Well, nested means that one is subset of the other or disjoint. But here it's really a chain. So if you take always the shore that contains S, then one will contain the other. So there will be a first one, second one. You can order them, and one contains the other. But sometimes maybe nested is used in this way, then it is nested, yes. Okay, so And we will have this notation. This is a vector that in our solution, actually in the previous one of 8/5, previous improvement, it played a role. It is the vector, the probability of an edge to be lonely, that it is the unique edge of a cut and a tree. So in other words, this XQF, this Q is a cut. It means the sum of the coefficients of trees which have only the edge E in the cut Q. Oh, there are many trees. There are some where E is the only edge, and we take the sum of the coefficients where it is the only edge. This is what it means. So probability, we don't use in a very essential way, but it provides simple notation and simple way of thinking about it. So this just means that the set of coefficients of trees which have E as the only edge in the cut Q. Okay?
What is script F?
Script F is the random tree, is the same as S. You're completely right that these two notations might unfortunately be confused, and it is confusing because we also have F now. But this should be S, so it's our random tree, a random variable, or tree-valued random variable.
Sorry, just before you move on.
Yes.
So in this example, we get these nested cuts, and we get one for every edge in the ST path in our tree, but that's not necessarily going to be true.
Pardon? We get...
So in this particular example, we get
right.
One for every single edge.
No, right. If we have this, if we have such a tree, such an optimal tree, then we are done actually, because only the narrow cuts are dangerous, and this tree, this particular tree is odd already in these cuts. So these are the cuts which have deficit in X star. So X star half is not a good parity correction vector for them. But X star over half is not also not necessary for this tree because it has already the good parity. So in the T-joint polyhedron that will correct this tree, we don't need these cuts. So it's a very good point. It's not at all always true. It would be very good if it was. It still is a surprising illustration of the method. But this example has this drawback that for this one, the parity correction, we can do the parity correction. But we don't do because we use the general methods that we use for trees which don't have this advantageous property too. So I wonder, yes, okay. Now we quickly go through the integrality gap version of the ST path heuristic. We proved, you remember, that 3/2 was true if f is equal to t, 5/3 if s is not equal to t, and then we observed that for the case s is equal to t, we have a even better estimation with using the LP relaxation. So saying that what we find is at most 3/2 the linear programming relaxation. We can do the same for this Hogevin's result by doing the separation that we did into P star and Q star, because on one hand we can take all the parts of the trees that don't contain the ST path, and that will have expectation X star minus P star. On the other hand, we can also take this average, this P star, and complete X star over half by this P star over half, which will complete it to the right vector. So X star over half has a deficit, but if you add once more, so it already has a P star over 2 part, but if for each tree you add the P star over the part, the ST path part, then it will add plus So it will add once more. It will add once more the ST path part of the trees, and so now with the ST path part, 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 a tree will intersect every cut in at least 2 edges, right? The problem was that some trees intersected some cuts in only 1 edge, but if you double the ST part on this tree, then now this tree will have 2 edges in that cut. So now every trees will have at least 2 in every cut, and so this average is at least 1 already, like S star over 2 was in the S equal T case. So this vector is also in the T-join polyhedron, in other words, because you have added once more. When there was only 1, then you added once more, so there was 2. And so if you take the optimum of the 2, that will be at most 2/3, so you get 2/3 of the fractional optimum as well for trees, and this is just good because this confirms that this way of thinking is not bad. Now, okay, so there are 2 inequalities related to this vector that we introduced. The first of them is that if you take this vector, that's already enough. You don't need P star over 2, but this smaller vector is already enough to complete your X star over 2 to satisfy the corresponding T-join inequalities, to fill the deficit that we had. And the reason is that the intuitive way of thinking, then you can follow it with a sequence of inequalities, is that, as we said, the guilty for having a deficit is that some trees intersect that edge, the cut Q in only 1 edge, but there, whenever it happens, and only whenever it happens, you double it. So just the argument I said for the previous transparencies, if you add it once more each time it happens, then you will satisfy the constraint. On the other hand, you can bound the sum of these vectors by P star, just because these events are mutually exclusive for different Q, and there must be always, these lonely edges might always be on the ST path. This is the unique edge of a cut which separates S and T, so they must always be in the ST path. Using these 2 things, the sum of these probabilities is at most P star. Okay, and now we get to, after having these notions, these were the preliminaries. But I started how much later? 10, 15 minutes? Okay. So now let's calm down and get to easy stuff. There are 2 conjectures. One is well known from long ago, is that the optimum for the TSP is at most 4/3 of the LP relaxation that you knew before, the sub-2 elimination constraints. And now the conjecture is that you have 3/2 for the ST path problem. And actually both are tight in the integrality gap sense. So there exist examples where you have equality here. Okay, we won't analyze example at this point. Do I want to say something else? Yes, the algorithm. Best of many Christofides, which was proposed by Ankleiber Schmois, and their analysis made the first progress compared to Hogeven's 5/3, and then I could improve that to 8/5, so 1.6, still using this algorithm. Now we will modify the algorithm, but this algorithm is simply to take these trees in our convex combination for X star, and for each tree, so not do as Christofides, that take the optimum tree for our weight function and then parity correct it, but for each tree, this polynomial number of trees, for each of them, find the optimal parity correction, and then take the optimum of all what you have in your hand. So polynomial number of trees, and for each of them you take the optimal parity correction, and you output the optimum of these polynomial number of tours that you got from trees plus parity correction for each. This is the best of many. Now we modify it with Anke, and we do best of many with deletion, BOMD. It's good that we didn't start with BOM-A, because then the next would have been very dangerous. So better not to speak about it. We start with C, BOM-C, and BOM-D. So X star is a convex combination of our polynomial number spanning trees, and we delete all the lonely edges of the trees, and that's why I like this example. But there was somebody who saw that for this tree you have a better parity correction than that, but never mind, we forget that, and we apply the best. I explained the best of many deletion algorithm on this example. So what will remain of the tree if I delete all its lonely edges, all the edges which are the only edges of the tree in the narrow cuts, in the pink cuts? Well, almost all of its edges are. And actually all of the edges of the narrow cuts are lonely here, so we delete all the edges of the tree. That's it. We deleted, only one edge remains, as you pointed out, some transparencies before. And okay, so now not much remain. But why we do this with this poor best of many algorithm that we delete? We do it in the hope that parity correction, because now these will be all, we have all bad parity, these cuts. We hope that parity correction will reestablish connectivity as well. So we'll spare, there will be some, that's not completely different, the goal of parity correct and to connect. And this is what happens, and the analysis shows that this is what happens. So what we do then is that we do parity correction for the forest. So for F, so we took a tree, this is the algorithm, we took a tree, we deleted all the, here is the tree, there you can't see it, but here is the tree. We deleted all its lonely edges, and then we parity correct the forests, not the tree. And try to prove that we reconnect everything, but it is not the case. So okay. So what we do is that if for instance, in our T-join, which parity corrects, if it contains only one, it is contained only in one narrow cut, then it indeed reconnects that narrow cut. The problem is if it is contained in in many narrow cuts, then there will remain some disconnected parts. But then we add edges which we deleted. If we had all, then if we had all the edges that we deleted twice, that will be certainly good, but we can spare one, right? We can spare one and an arbitrary one. So we can, so what we do then, if our sample, because T-joins also we will sample, we will we will have a vector which is x star over 2 plus something that we have to add. We will sample a T-join out of it, and whenever we have a bad luck and have an edge which is contained in several narrow cuts, then we reconnect all except one of the edges that we have deleted. It looks like very spoiling and very bad because we deleted, but now we had two copies. All depends on how often this will happen. And okay, now the step 2 anticipates the cost that an edge will cost us for these reconnection costs. So since one of them, and of course we will choose always the largest one, not to be reconnected twice, and we redefine the weights for the minimum T-join part, so that as to anticipate the cost that reconnection will mean for us. And so the first step is deletion. Second step is finding the minimum weight T-join with these modified weight, which anticipate the reconnection costs. Okay, now 3 is reconnection whenever the T-join did not reconnect. So we delete, then we reconnect with an optimal T-join with an anticipating cost, and then we have some components. It's still not connected, unfortunately, and now we reconnect, but here we can precisely optimize, right? If we have a graph with some component, then the minimum weight of an edge set which reconnects these components can be determined in polynomial time. It's just a spanning tree if you contract those components. So it's a minimum weight spanning tree problem. This you can now determine without extra tricks. And the thing is, so what is the... Right, so we deleted, now here's the repetition of all. Here is our tree. We deleted the lonely edges. We parity correct. These are the edges of TF intersection ST. So these are the vertices that have to have odd degree in the reconnection. The black ones, even degree. And here is the T-join that does it, right? So this has odd degree in the red vertices and even in the other vertices. And And here, there's the reconnection of the doubled edges, so this is the worst case estimation. In the algorithm, we don't care about this doubling and for every edge. In the algorithm, what we do is we take the components and we take twice, in order not to change the parity, we take twice the optimal spanning tree between the components. That way is just in the bound. And again, we can take for each spanning tree the optimum of normal Christofides algorithm, which we always took, the minimum TF-ST symmetric difference TF join, and take the optimum of the two kinds of solutions. So one solution is the complicated one, and at the end of all, we take the optimum of what we took until now, and for each tree, the best of many solution. So this is the algorithm, which is not so complicated, but still there is deletion in it. Now, in the analysis, I will just say what kind of things you have. When all the narrow cuts are pairwise disjoint, then reconnection does not arise, right? Then we don't have to reconnect. If the narrow cuts are disjoint, then the reconnecting edges will be contained only in one of them, since they are disjoint, they don't have common edges. And so there is no reconnection cost. By deletion, what is the probability that you deleted? Well, it's the probability that an edge is lonely, so it's exactly that. And the parity completion that we will add in order to satisfy the T-joint constraints will be this vector. So altogether, and there is no reconnection cost, so we have the goal in this case, when all the narrow cuts are pairwise disjoint. And actually it arises this case, all the narrow cuts. You can prove that if you have a 3-edge connected graph, and this was an open problem that I asked 2 years ago in Oberwolfach, also for the S equal T case, that if you have a 3-edge connected graph, then the all one function simply is a convex combination of ST tours. In the S equal T case, it is with 8/9 as a consequence of the famous conjectures. So it would be a replacement, an easier conjecture than if S is equal to T, then you have to write 8/9 the all one vector. On the other hand, here we prove the best bound for that case, because that case will satisfy that all cuts are pairwise disjoint. So at least there is a conjecture, there is something that we couldn't solve before that was known with the statement itself, if it was a conjecture, that follows with this method. Now, okay, in the general case, how do we get this mysterious 3/2 plus 1/34? Well, it is the minimum of two things, of a complicated thing and of something which we had before, so just to take the best of many solution. And this is what I said, so let us not go into the details here. This is just, okay. So this vector, you would appreciate it if you would have seen the previous one, which were much more complicated. This means that for cuts which are very close, which have a very small deficit, we just add a right proportion of the ST path. And now we have a smaller, because for them, none of the other tricks that we have are better. That for them, for cuts that have a small deficit, it is the best thing to do is to add a small proportion of the ST path. For the rest, these complicated looking vectors are rescaling of the vector xq that we had. That is a good parity correction, but now we have a smaller quantity to a smaller deficit, so we rescale and we add the right proportion. We have two ways of complete the vector x2 x star over 2, and this makes things relatively complicated. One, for the empty cuts that we have, they are also even cuts that should be odd. So for them we need parity correction and we need to complete xq, and for them we add one vector and we add another vector for the usual even cuts that we also had before. So we have two kinds of parity corrections to add, and we must be careful. And this is another issue why we have to distinguish two cases. And the issue is that the completion that we add shouldn't increase the probability of adding these bad edges, which are contained in several narrow cuts. So for the narrow cuts, so this vector x star over 2 has a deficit, and it has some bad edges, which are contained in several narrow cuts, but we won't have more. So in what we do, this is given by Woolsey or by Untitleding and Schmois, or whoever we cite, but we will not do any more harm by our vectors that we add, and that's why we have to be careful, and we succeeded in doing this, not adding additional vectors. And then if you take the expectation of the different cases, because we know they are relatively nice, the probabilities that the different cases occur, then you get, and that is what I say, that it's only 1/16 the number which actually occurs for this gamma. For this gamma vector, you have to separate what you mean by a small deficit compared to 2. So when do we use this path correcting parity completion, and when we use the other more tricky parity completions? And this separation is 1/16, which gives you the bound actually for our tours, for the complicated tours that we construct. If you look what it was, it gives you the bound x star over 2 plus the expectation of this, which is equal to 1/16 times p star. So the bound that we get actually is not such an ugly number as 1/34, but it is 3/2 x star. So the complicated construction is 3/2 x star plus 1/16 times p star. This is the bound, and taking the optimum of this bound with the other construction, with this rebalancing, with this other tree that we usually take. So that this other tree which takes the part out of the ST part of the trees, and which is 2x star minus p star. So this was the one we already had for the 5/3 estimation, this bound. Again, this arises by taking for each tree in our convex combination, doubling the part which is not on the ST path, which is a good parity correction. This is the expectation of the not ST path. So this is the weight function of this is what it provides as estimation, and 2x star minus p star is the other bound, and taking the optimum of 2x star minus p star and of well, for parity we are is that parity correction or yeah no, it's good, and of 3/2 x star plus 1/16 p star. If you take the minimum of the two, that's when you get the 1/34 bound. Okay. Now, just one more remark about the method, that the most difficult part is maybe to estimate the reconnection cost. And there it took much time to really realize the right way, which, with the help of which you get the same bound in the general case as is already necessary for some very special cases. So for some very special cases we had already this bound, and with this method we could generalize it for the general case, and this consists in defining the probability. We have some freedom, and here the probability way of thinking is really useful, is that when we have bad luck and we sample an edge for parity correction which is contained in several narrow cuts, then we have the freedom of choosing one of the edges. In the algorithm we choose the maximum weight edge, but in our convex combination, when we treat our convex combination and the analysis, we do not deal with weights. So we have the freedom of choosing the probability of edge deletion freely if we choose, but we have to be careful to delete only one edge. So the fact that these probabilities of reconnecting, is that the event of reconnecting, of not reconnecting, arrives on one edge only. So denoting xbq, the probability of doubling the edge which is in cut Q when sampling the edge B. This probability has to be at most 1, has to sum to at most 1 on all the cuts which contain a given edge E, and also in order to reach the goal you wanted, by the law of total probabilities, you get another linear condition that you want to satisfy, because this is a condition of probability. And so for the cut Q not to be used too much, you have another linear inequality. And using this method, you get that there exists a convex combination of trees with a simple bound. So there exists a way of choosing these deletion probabilities that the reconnection cost for arbitrary weights, so you don't have to suppose one given weight at one time, but you can reason only with convex combination that the reconnection cost can be at most x star over q minus 1 times the sum of these vectors xq. So in other words, without going into details, all the costs that we have can be expressed in terms of of the weights of these vectors xq, and it's like unit money, dollars, so everything is in dollars in coefficients of xq, and okay, this I won't speak about. This let me just say that you need somewhat particular convex combinations in order not to add, not to make harm, not to add with, by adding a parity completion, not to add anything to the probability of bad edges. And this particular convex combination was something that was used by Gottschalk and Figen, and that we could simply realize with matroid partition. So you just take different matroids instead of one matroid, and with the help of matroid partition you can have a particular convex combination of trees which makes possible not to add anything for the probability of bad edges with our parity completion. So to have only the vector x star over 2, only the bad edges which are already in x star over 2, which contribute to the probability of bad edges. Okay, now summarizing, and then we are done. We delete, we correct the parity with basic parity correction, adding x star over 2. For the parity correction with empty cuts, which are also bad cuts for us, they are even cuts. For the parity correction of other even cuts. And now particular convex combination of trees makes possible to have only the basic parity correction as a probability of bad edges, and our randomized reconnection with the probabilities given by an LP give you good enough reconnection probabilities to reach the ratio with this expectation, and then to take the optimum of this and this other solution given by the best of many algorithm, you get the ratio that I gave. Not so simple. On the other hand, if you forget about deletion and you just apply the framework, and maybe that's what I should have started with, but then we spend almost all time with that, then you don't need to reconnect if you don't have deletion, and you get the 8/5 bound in a very simple one-page way, which if any of you would download our paper, it's one page in it, and with a bound, which is, of course, it's just 2 years old result, but gives already better than Hogeven, and you can experience the other ideas which are not related to edge deletion, and until then the algorithm is simple. That can be taught at a course in half an hour, say. Okay, so what makes possible the improvements compared to earlier results? The deletion of lonely edges, the randomization with these lonely parameters, and that this completion, these things that we add, don't add to the probability of these bad edges that are expensive to compense. And this is the last transparency about the history. And as I can see, indeed, you are tired enough, so you don't want any more technical transparency. So there was a big silence for 20 years, more than 20 years, and some quite ingenious setting was proposed, and the bound was improved by Einkelberg and Schmois. It was general. Pardon? Yes, it's Hyung Chang. Yes. Hyung Chang, who gave a seminar here a month ago or so. Yes. And actually, yes, I first heard David Schmois, and then I heard Hyung Chang also at ISMP in Berlin 4 years ago. That's why the 2 dates mean that they first appeared in some volume, like here it is stock, and then in a journal. So otherwise, if you put only one of the days, there will be contradiction. A result using another was published earlier in some journal. So yeah, then Joseph Cherian, Zach Frickstad, and Jean Tao? Yeah, I'm just confused. Anyway, yes, Gao proved it for, generalized it for T-tours, and then there were results only for the metric weights. The bound feet half could be reached for the graph metric case when your metric function comes from shortest path functions of graphs. Then for general weights 8/5, but with the same algorithm, still with their algorithms. Then Jens Figen and then Gottschalk and Figen improved the bounds with some reassembling ideas which were very complicated. But on the other hand, the idea of having special combinations of trees which made us possible to spare our completion costs come from here, and now we have this bound in. Well, it's not simple, but there are in the details there are not so many technicalities. I think it's readable. Thank you very much. This is the end.